So, particle physics, huh? You're braver than I am digging into this FCC-ee report. FCC-ee, the Lepton Collider Future Circular Collider Conceptual Design Report, Volume 2, if we're being exact,
Yeah, it's a bit of a mouthful.
to say the least. Glad to have you here to help us break it down.
Happy to be here. It's exciting stuff, actually. This report, it's basically a roadmap for the FCC-ee project.
FCC-ee, that's the proposed electron-positron collider, right?
Right.
Trying to one-up the Large Hadron Collider.
That's the one. Though it's more like building on what the LHC started. See, the FCC is all about precision. It'll be smashing electrons and their antimatter buddies, positrons, together, just like the LHC, but
Higher stakes.
higher resolution. Think of it like,
Okay.
the LHC gave us a blurry picture of the universe, right at its smallest level.
Yeah.
The FCC-ee, it's aiming for 4K, crystal clear.
Okay, so we're zooming in on the universe's tiniest particles. But why? What's the big payoff in seeing them with such incredible detail?
Because those tiny particles, they hold the secrets to, well, everything. How the universe works, why things have mass, maybe even new forces we don't even know about yet.
Hold on, new forces. We're going full sci-fi now.
That's the exciting part. This
Okay.
kind of research, it has the potential to completely change our understanding of, well, reality. It's
Yeah.
like discovering electricity all over again. Who knows what we might find, what technologies we could unlock.
Okay, now I'm hooked. Let's get into it. So this report, it's diving deep into the weeds of what the FCC is going to be looking at, right?
Yeah, and one of those interesting things is just how precise this thing is supposed to be. Like, mind-blowingly precise.
Okay, give me an example. What kind of measurements are we talking about?
So they're talking about measuring something called the Z invisible width. And get this, they're aiming for an uncertainty smaller than 0.0008 of a standard model neutrino partial width.
Uh-huh, right. And for those of us who didn't major in particle physics, what does that even mean?
Fair enough. It's complicated, but basically, imagine you're trying to measure a grain of sand on a windy day. The Z invisible width is like that grain of sand, and the wind is like all the uncertainty. The FCC-ee is like a super high-tech wind blocker.
So we can finally get an accurate measurement of that grain of sand, or, well, the Z boson. Why go through all that trouble, though?
Because, and this is the exciting part, those super precise measurements, they could reveal cracks in what we think we know about the universe.
You mean the standard model. That's like the holy grail of particle physics, isn't it?
Exactly. And it's been incredibly accurate so far, but it can't explain everything. So we push it to its limits, look for those tiny inconsistencies. Those are the clues to what's beyond the standard model.
Like what kind of clues?
Well, take the Higgs boson, for example. The LHC, it discovered the Higgs, right? But the FCC-ee,
Yeah.
it's going to be Higgs factory, churning them out so we can study them in way more detail.
More Higgs bosons, more problems.
More like more answers. See, one of the things they're trying to pin down is the trilinear Higgs coupling. Basically, how strongly the Higgs boson interacts with itself.
And why is that important?
Because, and I know this is going to sound weird, but
Yeah.
the Higgs boson is why things have mass.
Okay, yeah, that's pretty important.
Right. So by understanding how the Higgs interacts with itself, we're basically understanding the fundamental nature of mass. The report says they're aiming for a precision of plus or minus 42%. That's a huge improvement, and it could point us toward new physics.
New physics, like what? Give me the sci-fi version.
Think extra dimensions, parallel universes, stuff we haven't even dreamt up yet.
Okay, hold on. Extra dimensions. Are we talking like a secret portal to another world kind of thing?
Well, not exactly. Some theories suggest that there could be more spatial dimensions than we can perceive, curled up at an incredibly tiny scale. Like, imagine a garden hose. From far away, it just looks like a line, right? But up close, it's got this whole other dimension curled up in a circle.
So we're trying to find those tiny curled up dimensions that might be hiding right under our noses.
In a way, yeah. The FCC-ee might be able to indirectly detect these extra dimensions by looking for particles that seem to, like, disappear or pop in and out of existence. Like they're taking a shortcut through these hidden pathways.
And that's how we could find evidence for, say, a parallel universe.
Maybe. Or something even wilder that we haven't even thought of yet. They're going to be using something called effective field theory to make sense of it all.
Yeah.
It's all about finding those deviations from the standard model. Those deviations, those are the clues to new physics.
Okay, let's talk about actually building this thing because, getting those precise measurements, discovering new particles, it's got to be a beast of a machine. What are we talking about here?
It's a massive undertaking, for sure.
Yeah.
The report, it goes into a lot of detail about the engineering challenges, and honestly, some of it's way over my head.
Right. Well, luckily, our listeners are a smart bunch, Give us the layman's version. What's going to happen to make this FCC a reality?
Well, one of the biggest things is they need a ton of collisions, right? Like an insane amount. And that's all about luminosity.
Luminosity, right. That's
Yeah,
like how bright the collisions are.
kinda. It's more like how many particles are packed into the beams and how often those beams cross paths.
Hmm.
More collisions, more data, more chances of spotting something interesting.
So more is better. But why is it so hard to get that high luminosity?
Think about it. You're trying to smash together these tiny particles, right? At practically the speed of light.
Yeah, sounds tricky.
It takes incredibly powerful magnets to even aim these beams, let alone make them collide at the right spot. And the FCC-ee, it needs way higher luminosity than anything we've ever built. It's like pushing a shopping cart at walking speed versus racing a Formula One car. The forces involved are just immense.
Intense. So high luminosity is one thing. What else?
Synchrotron radiation's a big one.
That's the particles losing energy as they go around the curve.
You got it. Like,
Yeah.
imagine running a marathon, but every step you take, you get a little bit more tired. The FCC has to deal with that energy loss. They've got to keep those particles energized, focused. It takes super precise magnets, vacuum chambers.
Wow. Sounds like they thought of everything.
Well, almost everything. Dynamic aperture is another big one.
Dynamic. I'm going to need a visual on that one.
Okay, so imagine like a marble rolling around in a bowl. Dynamic aperture is like how big that bowl needs to be to keep the marble from flying out.
Ah, so the beam has got to stay contained.
Exactly. And the FCC, it needs a huge dynamic aperture. So they're using like crazy computer simulations, even AI, to make sure everything is aligned perfectly.
AI designing a particle collider. It's getting hard to tell the future from a sci-fi novel these days.
Tell me about it. But even with all that, the collider's just one part of the puzzle, right? They also need these incredibly sophisticated detectors to actually see what happens when those particles collide.
The detectors. Okay, now that's something I'm a bit more familiar with. So what are they working with?
Two main concepts, actually. CLD and IDA. Think of them like high-speed cameras,
Yeah.
except they're capturing particles instead of light.
Okay, so what's the difference between the two?
CLD uses a more traditional design with a silicon tracker and a calorimeter. That's for tracking the paths of charged particles and measuring their energy.
Got it. What about IDEA?
IDEA is a little more innovative. It uses a different type of tracker and a more advanced calorimeter. It's a bit more complicated, but potentially more cost-effective, too.
So different approaches, but same goal, capture the most data possible from these collisions.
Exactly. And the really cool thing is this isn't just like one country going it alone. It's a massive global effort. Scientists and engineers from all over the world working together to make this happen.
That's the thing about science, isn't it? It brings people together.
For sure. And the benefits, they go way beyond just particle physics, too. I mean, we're talking advancements in computing, material science, all kinds of fields.
It's like a ripple effect, right? The knowledge gained here, it could lead to breakthroughs we haven't even imagined yet.
Who knows what the future holds? That's the best part.
Well, one thing's for sure, this deep dive has been a wild ride. From the tiniest particles to the most massive machines, the world of particle physics is full of surprises. Thanks for guiding us through it.
Anytime. This stuff, it's exciting. Gets me fired up just thinking about it.
And to our listeners, keep those questions coming. Until next time, keep exploring.